organizing this wonderful conference, and thank program committee to giving this opportunity to present our work. This is a joint work with my student Jay, also in the audience. Here is the archive number. The title is little different from our original Beyond ID submission. Okay, I will start with Shannon's noisy coding theorem. To send k-bits message through and copy identical channels, Shannon tells us that there exists a sequence of codes such that the error probability vanish asymptotically if the ratio k over n is smaller than the channel capacity for all n. Later, the HSW theorem generalizes the result to the quantum channels. However, the two results do not tell us how fast the error converges to 0, so we do not know the convergence rate. Okay. Then later, there are many people study these two important operational quantities: bit rate versus error rate. Bit rate is number of bits per channel used. Error rate is the convergence rate. The channel capacity here is the first order of the IID asymptotic expansion of the maximum number of bits if your error tolerance is a fixed constant between 0 and 1. On the other hand, if the rate is fixed, then the optimal conversion rate of error is the first order of this quantity. In this talk, we will not talk any higher order terms. We will only focus on the first order terms. Okay. If you plot the optimal trade-off between a bit rate and error rate is something like this. It's not fully known yet, even in the classical case. People only can fully categorize this if all the optimal error exponent, or we call a reliability function, for certain high rate region above some artificial critical rate. This point is called the error exponent at 0 rate, and which corresponds to the sum of exponent mentioned in binary hypothesis testing mentioned by Ludovico yesterday. This point is the channel capacity or stance exponent, which is the minimum rate such that the error exponent is 0. So stance exponent and sum of exponent lies on the two extremes. In this talk, we'll study this region, the optimal error optimal trade-off between bit rate and error rate. Okay, so after 1948, for instance, Shannon himself, Gallagher, studied the convergence rate of the errors. In his papers in 1965 and later in Gallagher's book in 1968, Gallagher provides a very beautiful bounds, holds for any input distribution for which you use as the ID Renner code book and any copy of channel, any code length. So essentially, his bound is a one-shot bound and holds for any shot. This expression is like a power mean, and by Jensen inequality is less than 1. So it is a multiplicative upper bound for the error. And later by Shannon, Gallagher, and Berkeley show that this convergence rate is optimal for rates above the critical rate. So that's Gallagher's random coding bound for classical channels. So after the HSW theorem, Bernachev and Holevo in this 1998 paper, they conjecture exactly the same bound, but they say that they seek some constant C such that this holds for all n and replace the channel output distribution by density operators. So it's very similar form. And I just write n equal to 1 because it's essentially one shot. And later, by using the substance identity from Rakonik and Stephanie Renner in 2009, this form can be rewritten as a we call a Pets-Rennie mutual information. The exact definition is not important right now, but you can see as this quantity is additive, so it's a multiplicative upper bound. So that's what Bernachev and Holevo want to do. They want to generalize Gallagher's random coding bound to classical quantum channel. Later in 2007, Hayashi has an error bound, and it's also multiplicative bound. It's additive here. Holds for any distribution, but the form is different from Gallagher and Bernachev and Holevo. So even in the classical case, it's non-type, but it's the first exponential decaying bound for classical quantum channel in 2007. Later in my paper, I can slightly improve this constant 4 to be 1. Okay, so let's talk about converse a bit. Actually, in Andreas' PhD thesis, he already provides some converse bound, the upper bound, the optimality bound to the error exponent. In terms of this one, well, in his thesis, he used the Hamiltonian form, but later we realized, oh, it can be written in terms of like log Euclidean Rennie information. Okay, later in 2013, Dalai shows another upper bound in terms of Pets. We know that this local Euclidean is larger than pairs for alpha less than 1. So this bound is slightly tighter than the previous. So that's why we want to pursue for the pairs Renner divergence in this form. Later in 2024, Sama and Marco, they show a very beautiful one-shot bound. It's very clean because they got constant exactly 1 and holds for any input distributions. But in terms of the measure the Renner divergence is also a one-shot bound. And they use some called Beggy-Thomas-Michael operator in inequality. In the commuting case, it exactly covers Gallagher's Renner coding bound, the classical case. Another breakthrough is by Joe in his ITW paper. Actually, it's Beyond ID talk 3 years ago. He realized this duality between channel and preference simplification a long time ago, and he realized, oh, you can use this observation by duality, and then by applying Hayashi's bound for preference simplification, can be used to prove error bounds for channel coding. So essentially, obtaining this bound is like a pinch-in factor because it comes out from Hayashi's bound. And this holds for uniform input distribution. It's also a one-shot bound, but it has this pinch-in factor. But it got this precise pairs Renner divergence. And so essentially, Renner's bound is optimal for symmetric error exponent for symmetric channel because uniform distribution is exponent achieving. But for ID channels, this pinch-in exponent is only polynomial. So later, by adapting Gallagher's input shaping method, and also independent by Li and Yang using a kind of method of types, they can approximate any input distribution, but go to asymptotics via input distribution. So these two papers push the result further to asymptotics. So the result shows that the optimal error exponent for CQ channel is asymptotically achieved, but Bernashev-Holevo's one-shot conjecture for Renner coding bound still remains open. So that's the history, that's the progress. I want to comment that later I realized that, oh, actually in classical setting, there are many other different input shaping methods, and there are some pros and cons of practical considerations studied by Ubenke. But we don't know about classical before, coding theorists. No. Okay, so why this problem is so challenging is because essentially it's like a large differentiation analysis. And yesterday we already know, oh, there are some Shannon approach or some other approach. In information theory, you know, Sisa and Corner is like using the proposed method of types. Basically, it's very similar to Shannon's approach in statistics and probability. So in classical case, they show something like this. This is the Hamiltonian form. Actually, that's the exponent obtained by Andreas. So this is like a log Euclidean Renner divergence. We know that it's larger than the pairs 1. But because Datta already showed this is the upper bound, so if we use their method of types to get something like this, it's too good to be true for achievability because of Datta's impossibility result. So basically, we don't know if any such Shannon's method of types works for the error exponent. It works for channel capacity because alpha goes to 1, these two quantities are the same. But for fixed alpha, we don't know. So basically, half of the method in the classical regime doesn't work, may not be working here. So another way is by Gallagher's method of maximally likelihood decoder, it's similar to Cramer's approach of using Markov inequality in probability theory, but unfortunately, we don't have quantum maximum likelihood decoder. It means that for any realization, why we choose the best X such that has the largest likelihood, but in quantum case, they do not commute, so there's no quantum maximum likelihood decoder. So that's why this problem is so challenging. Okay, so our main result is to show Bernashev-Holevo conjecture with the dimension-independent prefactor C. It will be explicitly determined later. So this result can be viewed as a Gallagher's Renner coding bound for classical quantum channels. And then we realized that we can do beyond Bernashev-Holevo conjecture. For instance, constant composition code, this can be viewed as a Sisa-Corner's Renner coding bound for constant composition code. It's optimal for any composition and provides new operational interpretation for quantity code pairs Augustin information for alpha less than 1. For alpha larger than 1, the operational interpretation has been found by Milan and Ogawa. And also classical quantum significant Wolf coding, both for fixed length coding, variable length coding, and for communication over fully quantum channel without or with entanglement assistance. The main technique developed by us is what we call the operator layer cake theorem. It says that the directional derivative of operator logarithm has this integral form in terms of the projection between A and B. That's our main technique. Okay, so let's conclude what we want to do. Essentially, we want to study, to send qubits over a quantum channel. We don't need to impose any ID assumptions. Then how small the error probability that we can achieve and how? That's the central question. You don't need to know the notion of capacity or whatever. We want to ask this question. And if we are lucky that the underlying channel have some product structure, then what's the error behavior? That's the central question. To answer this question, this leads to the part 2 of our talk, the quantum states discrimination. So if we have an ensemble of quantum states with prior probability px and the quantum state, we want to perform some measurement to figure out which x is. The optimal error is given by this. But unfortunately, we don't have a corresponding expression for the optimal measurements. We can run some SDP to get some approximate numerics, but when we tell the quantum engineers to do some circuit synthesis for those numerics, it could be quite expensive. If our system is like dozens of qubits, like 30 qubits, it's also not easy to run SDP. So people come up with other suboptimal measurement called, for example, by Belafkin, it's called pretty good measurement with respect to this quantum ensemble defined by this way. So it's very intuitive because this is linear in the numerator. You can summarize over OX, it's a P of n. Okay? Then by boundary and Collier, we know pretty good measurement is pretty good because up to a constant 2 to the optimal error. For example, we can check see John Waitrous' book. And why this pretty good measurement is pretty good could be, probably we can see this from the classical stochastic likelihood decoder because it's like for any realization, we choose the x, the probability is proportional to the likelihood. So it's like this quotient. So I think the idea is very similar to the classical stochastic likelihood decoder. However, in quantum setting, this one, if we put emphasis into alpha power, we call that the alpha-weighted PGM or alpha-powered PGM. That will be used later. In a quantum setting, the quotient is not unique due to non-commutativity. And in Lieb's famous concavity paper in 1973, he realized that the derivative of operator logarithm can be viewed as the quotient because the derivative of log is like 1 over A and B the direction. Has derived this integral formula. So back in Thomas paper, they use this kind of pretty good measurement defined by this quotient. I will use this for short for this derivative of A with direction B. Okay. And I want to point out at this moment that if we consider success probability, there are actually a relation between a standard PGM and an integral PGM. This can be written as a collision, quasi-collision divergence studied by Renato. And this both ways Q is defined by this. We also satisfy data processing inequality. But I think in the quantum metrology community, people already know there's a relationship between these two quantities via the quantum chi-square divergence. Or we can just prove it by hand. So it means that this success probability by the standard PGM is larger than the integral one. So we have a small conclusion here. In practice, we just apply the standard PGM because it has better performance according to entropy inequality, and it's a known algorithm by Gideon et al. So we just apply it. However, this integral PGM serves as a very good proxy for analysis later. If we can show that by using this integral PGM, the performance is very good, it also guarantees that using a standard one is also pretty good. So in the following, we'll just focus on this integral one. Okay, and later we'll go into the binary hypothesis testing because that's the core of our solution. I will show how to explain the quantum channel van Aldernas inequality to you, and I want to mention one important thing. By ignoring the prior probability, we'll only add up a constant factor to our error bound, and why pretty good measurement is also pretty good from another angle. So for the binary hypothesis testing the price p and small p and small q, we know the error probability, optimal error probability is written in this form, and the famous Holevo Hao-Chung theorem shows that the optimal one can be achieved by the projection between the blue operator minus the red operator will take the positive form. So this error probability can be written in this form in terms of trace distance, and this projection can be viewed as a quantum Neyman-Pearson test because we choose the region, in the classical case, we choose a decision region such that the likelihood ratio is greater than 1, so it's a quantum analog. Okay. In the n-copy setting, we have this error bound. Unfortunately, this bound is not multiplicative. even if we have a closed form expression, but when n is large, it's difficult to compute this quantity. So that's why the chain of bound is important. In 2007, 2008, they proposed this upper bound. We put this prior P and Q out. This is just some constant smaller than 1. However, this quantity is multiplicative. So we have exponential decay bound. 1 year later, by Nussbaum scholar, they show that this exponential decay rate is optimal. One observation is that this exponent does not depend on P and Q, the prior probability. So that's what we learned from their result. It's easy to see because if you consider any P and Q, just the optimal Holevo-Hao-Chung measurement, if we put the wrong, if we apply Holevo-Hao-Chung measurement with the wrong priors, for example, 1/2, it's also fine because we can push the small p and small q to the maximum of lambda, then it becomes like 1/2 here, 1/2 here. But this even prediction Holevo-Hao-Chung measurement is optimal here. So essentially this one. So it's sufficient to consider just the even case up to a constant. That's a known factor in the community. I want to mention this because we'll use this observation later. Okay, so let's see what's going on in quantum kernel form. Let's make a naive attempt called like a change of measure argument. The type of error is like this. Because of this projection, we can move this rho to sigma. It's very easy to see because you can find a difference of this and it's positive. You can throw away this projection to get trace of sigma, but this trace one is a kind of trivial one. If we do it smart way, we call that tilting. We compose this rho to rho alpha, rho 1 minus alpha, and by the help of this projection, at least in the classical setting, move this rho to this sigma 1 minus alpha. We can throw this away easily, and it becomes a multiplicative bound. I think that's the spirit of kernel bound. We choose the optimal alpha between these, such that it becomes multiplicative. It's like the Markov inequality in probability theory in exponentially time. However, this is not what ordinates did in their paper. In their paper, they show this, what I call ordinate trace inequality like this one. It's kind of difficult to see what this telling us. So my way to see this is that we parameterize those things to this guy. This A is like a rho, and use the projection alpha powered projection. Let's assume it's true. Then, so what they did is not they relaxed. They didn't directly analyze the optimal measurement, but through this we call it alpha Holevo-Hao-Chung measurement like this. And by using this bound, then get multiplicative bound. We can see easily. So what is going on here? Let's see. We first decompose A to A minus alpha S for S between 0 and 1, any S parameter that we call tilting parameter. And with the help of this projection, it's kind of we want to move this A to the alpha power to the additional S power to B to the alpha power times S power. And actually in here I page 2, they started to strengthen ordinate inequality. So actually we can do this by the result. So we move this, we get this one. So in ordinate inequality, they prove this inequality specifically for this spatial S. And you put it in this S, you got this one. That's the right-hand side. So that's how I interpret their result. They are kind of doing some tilting to get some multiplicative bound. That's the essential part. Okay, so let's go back to the integral prediction measurement, and I need to use the opportunity to introduce the operator layer cake theorem. So we use this. Okay, let's see the expression. The full version is like this. From this B is Hermitian, not necessarily positive. And in the classical case, this formula is actually intuitive. We use a name by Lieb's textbook. In this theorem, he said that for any measurable function has this indicator expression called layer cake representation. It's easy to see. Let me show you. So this is a function. We integrate, for example, with respect to the bag measure. So it's like this. The weight is the mu, and the height is f of x. But we can also integrate horizontally. The height is dt, and the width is the measure of this event f t below to f of x. And because the area are the same, so they are equal. So that's why they call this layer cake representation for this function. So we just use the same name. Okay, so let's go back. Okay, in statistics, it's also very often to express the expectation in terms of the cumulative functions. But here, we can take this random variable to be a quotient or likelihood ratio. So you see the formula, like this projection. And this quotient is like d log. So classically, it's very intuitive. When B is positive, then the second part is 0, because for then every negative U, then its projection is 0. We can simplify the version like this. Okay, but the quantum version of this formula is actually non-trivial, because every projections parameterized by this U, they are not commuting. So we cannot just apply classical method. So this eigenprojection is tilting all the time continuously along U, and there are some jumps. So it's non-trivial. Okay, let's see how this comes into play. Oh, I also want to mention that this the formula corresponds to the D log, not the standard symmetric quotient. So that's also that's also non-trivial to see. So that's why this comes into play. So if we consider this integral predicament test, I will just put the denominator here, a plus b, and we can restrict this integration interval to 1 because this small operator norm for this smaller than 1, for u larger than 1, projection is 0. Then we put this b to the right-hand side, so it becomes like this. And use any number in 0 and 1, so it's like prior probability, put u and minus u to the other part. So that's how I see this. For u drawn uniformly randomly, and for example, the realization is 0, so we put all the weight on sigma. So like prior probability put. We can still, other realizations are tilted back a bit, and for other, we have different tilting. So the statistical mixture of these loss projections gives us this test. So that's how I feel this equality, this means. Okay, so it means that the integral PGN is actually the randomized version of the Holevo Hao-Chung measurement, because by the previous formula we have this integral, and we can put this integral outside. So essentially we are applying Holevo Hao-Chung measurement, and stochastically we draw random priors. So this gives us some observations. We can simulate integral PGN by randomized Holevo Hao-Chung measurement. And we also know that integral PGN is suboptimal in the sense that we lose the prior information. If we knew the prior information, we just apply the exact Holevo Hao-Chung theorem. But we don't know the prior, just random. Okay. But wait, we already mentioned that if we apply a Holevo Hao-Chung measurement with the wrong prior, it's okay, because it's essentially optimal up to a constant. Let's see. So this is a type 1 error via this integral PGM. Then we just use the layer cake formula. Okay, but this is a wrong prior. But this is wrong prior for each integrate up to some constant. I just put big O1 here for simplicity. Integrate this guy is big 1. So it's essentially optimal. This provides another way to see why integral PGM is pretty good, because essentially it's optimal up to a constant. Okay, so let's summarize so far. We use this. We call this extremal decomposition for the two-outcome integral PGN in terms of the optimal Holevo Hao-Chung measurement. And we know that the wrong prior only caused a constant error. We know Chernoff bound, and we know ordinate Chernoff is a bit different because we use this alpha version. We will use this in our solution. Okay, so let's go to the third part of the proof. The coding is basically the same as people did before. We use the pairwise independent random code book. For any uniform message, we pick a code word according to some distribution, and it's pairwise independent. For the decoder, we use alpha integral PGN with respect to a realization of the code book. So essentially, suppose this send message and that's our alternative, and we apply the integral PGN like this. It's like decide this way, and the complement of the P of an element is like this, deciding the other way. So essentially, we are still using this 1 versus the rate, this binary classification method. So let's see the proof, the error analysis. Let's assume that x1 is sent, then by Wong's rule, and we put in the alpha integral PGN here. So we got this formula. Okay. Then we just apply the layer cake theorem. This B is the numerator part, the whole rate part. A is this part. Oh, sorry, this part. We just play with this quotient. So we directly apply the operator layer K. We obtain this guy. Okay, and here we already reduced to binary hypothesis testing. Okay, then we apply ordinate inequality. This A is this blue guy, and this A alpha, B alpha, this B alpha. Then obtain this multiplicative bond like this, with some constant multiplicative term because of the wrong prior here, U. Then because everything is random, so we just put expectation everywhere. Then we move this the other part expectation inside, because we are alpha is greater than 1/2 and less than 1, which means that 1 minus alpha of alpha is between 0 and 1. It's an operator concave function. We put this expectation inside by Jensen inequality, we are in the right direction. So here we take this expectation. So we got n minus 1 many, this expectation of powers. But the right side is also, outside is also expectation of a power. Here is a power 1 minus alpha over alpha. This is power 1. So we combine them to our final result. That's Beneshev and Gallagher's expression with a constant, dimension-independent constant. So essentially, we only apply ordinary inequality and concavity. The proof is actually almost immediate if you really understand what's going on in those binary hypothesis testing. Let's review the whole process. This is called a general recipe for one-shot quantum information theory. So my previous paper showed that we want to reduce the general quantum information theoretic task to quantum hypothesis testing. We can use PGM because it serves as very good uniform bound because it's like 1/3 of the rest classification. However, if you are doing achievability, if the resulting test here in binary hypothesis testing is already very bad, then you can get very bad performance. Or if the test there is ugly, then you probably very difficult to analyze. But our contribution is to show that when using this reduction to the binary hypothesis testing, the test resulting effective test layer is essentially optimal. In the sense that we have some wrong price, but it only costs a constant multiplicative term. That's our contribution. So essentially, we do not have maximum likelihood decoder in quantum setting, but we do this all again. Then we almost arrive at the stage as if we are using maximum likelihood decoder, because in the end we get some projection. We can use many already existing results there to derive the error bound. So that's the whole story. Okay. So I want to point out one thing, comparison to Hayashi's exponent. Hayashi's exponent look like this. We know his exponent is not type. This is our exponent, Beneshev Holevo exponent. When I was a student, I read Markov's book. There are many inequality between the up arrow, down arrow. But I don't really understand what's going on here. But if we reparameterize Hayashi's bound, such like, we can rate is the same prefactor, and we only need to compare this I. It's actually this. But here is conditional entropy, but Hayashi and Markov has some paper to do this, to show the duality for the mutual information. We can directly see, they are equal. So I think Hayashi already know this, but it's worth pointing out. Let me see. Okay, still have some time. Then let's take a closer look at this prefactor constant term. So the constant, if you keep tracking the constant all the way, it's like this. It depends on alpha. For alpha larger enough, it's kind of okay because it's below 2. And this holds for any alpha. And for your rate is larger, this is like a critical rate, this rate approach to a channel capacity. If the rates are large, then it's kind of okay because it's below 2. And you can afford those bad constant here. But when in our original BND submission, we are not very happy about this bound by applying ordinary inequality. And in our archive version, we provide another bound without using ordinary inequality to get this. And this looks interesting because in this region, it's kind of even better than Gallagher's bound, because Gallagher bound has constant 1. Here, it's constant below 1. And because these two bounds hold, we can just choose the worst case between them, to choose a minimum between them. And the worst case is something like this, and it's below a constant like 1.012. It's not perfect here. It's very good here, but it's not perfect here. But we can live with it. So that's how we address Beneshev and Holevo's conjecture to obtain a dimension-independent constant like this value. I believe there's still some room for improvements. Okay, so I want to show other implications. So in my previous paper, we studied one-shot channel capacity. We know there's a very essential inequality here. I want to show you that we can also reprove this by layer cake. So actually, this is the inequality I proved in my paper. Later, Markov, Salmon also proved this by integral 1 in the middle by adapting the method. But we can see that this has an optimal error, has a layer cake representation in terms of projections. We can prove the hockey stick divergence and to see this. And for this one, by layer cake, for this one, then you can see they are very similar, only different by this 1 minus U and B. So this inequality is true because of a kind of relaxation, because this map is monotone increasing. It's not obvious because projection-wise, it's not monotone because the eigenspace changes. But if multiply both sides by A and taking trace, it's monotone. And it's interesting, and let's see this more. And actually, this monotonicity is equivalent to the convexity of the hockey stick divergence mentioned yesterday by Christophe. And it's also equivalent to another quantity called information spectrum divergence proposed by Hayashi and Marco. And this quantity is increasing in epsilon. So on Thursday, we'll see in Bartosz talk, like there are many smooth quantity, and for any very smooth quantity, if you relax the error tolerance, error ball, then the distinguishability increase. This is also true for hypothesis divergence, also information spectrum divergence. The second implication is that in Marco and someone's paper, they have this operator inequality. It looks surprising, but it's true proof in their paper, and actually not long. But we can also see this by layer cake. This we just put this that we use formula we used before. Then we do some parameterization by this phi larger than 0, and this 1/1 plus phi less than 1. We just throw away by upper bound this by phi. But this is just layer cake. So we can see why the operator inequality is true just by layer cake, by do some relaxation. So the point is not to reproving the existing result, but once you know this increasing map, you can just play with elementary calculus, and they provide new bounding techniques, like for example, like operator inequality. So that's what I want to share. In our follow-up 2 papers, we'll kind of use those to improve some known inequalities. Okay, so our result extend beyond classical quantum channels. So for any fully quantum channel and any quantum ensemble at the input, you can prepare these holes. If the channel is product, not necessarily ID, we already have some multiplicative bond. But of course, if we want, I guess this can be seen as a alpha version of the Holevo quantity, because alpha 1 Holevo quantity is not additive. I don't expect it's additive, but in my opinion, we only need regularization in the converse. For achievability, the bond holds for any quantum ensemble. You don't have necessarily to prepare some entangled ensemble across several input. You can pick one. You can just pick one. And if the channel is nice, some product structure, we have multiplicative bond. So that's why I prefer to write everything in terms of like this, and without optimizing everything, because I don't want to force like experimentalists and practitioners, engineers to see, oh, we need to optimize. We don't. Actually, we don't. Okay. For entanglement safety case, for any entanglement like prepared by between Bob and Alice, then we have this multiplicative bond. And by the quantum Simpson identity in Marco and Hayashi's paper, we have shown this Page-Rennie information, and CFI is the same as before. Okay, so that's our bond. Okay, so let's go to conclusion. So to answer this question to send k bits through a quantum channel, not necessarily ID, then what can we do? So like this is how I can imagine in reality. So there's some channel noise across some qubits to qubits, some bigger noise, and maybe some product, hopefully. Then we can naively apply measurement like product measurement, each one. So it's like parallel transmission, parallel encoder, parallel decoder. If your quantum device is powerful enough to implement a large particular measurement across all the channel outputs, it's still finite. If you can impose this, then at the input, you can prepare product ensemble. It's already very good in the sense that you have multiplicative bonds. Of course, if you want to get larger exponentially decay, okay, I want to mention that this becomes multiplicative bonds, then the error bound becomes like a multiplication product of several terms, only depends on their local dimension. So that's why this multiplicative bond is already useful to me. Of course, you can optimize further, but you need to know which direction to optimize, which quantum ensemble you want to prepare. You can, of course, prepare very large entangled ensemble can increase your decaying rate, but then the quantity you want to compute this quantity. We do have an analytical form, closed form expression, but it depends on the whole dimension. So the point is, I think in achievability, the bottleneck is really at the output, the critical measure, how large critical measure you can prepare. At the input, if you can do the best, but the product also already very good to me. Okay, so I still have 5 or some minutes. Let me go to show you some ideas of the layer K. I don't have time to go through the whole proof, but we have 2 proofs, and I want to show you that how we can get this d log. There are main 3 steps. The first step is like to express this projection in terms of a contour integral in this way. And this is actually not difficult because you just view this as a diagonal matrix, B minus UA, the whole thing as a diagonal matrix. Then you can use compressed analysis to see this. And this integral is overall simple contour enclosing the positive spectrum of B minus A. So we can have this formula. Basically, this just it's not hard. Okay? And why we want to use compressed analysis is because this integration region depends on the parameter u, and that's not nice. We want to enlarge this region to some r, big enough than the rightmost eigenvalue. So still, by compressed analysis, it's also true. For all u such that it's non-singular, the pole doesn't touch this origin, so it's like semi-disk on the right side. And why we want to do that is because we want to exchange the integration. I think that's the spirit of the layer cake theorem, at least in the classical setting. So we integrate this for all u except for u such that this is singular, but let's discrete measure 0. Say we use Lebesgue integral sense like this. Then we exchange this by Fubini's theorem, but of course we need to check the absolute integrability. So after exchange this, we integrate this guy, but this is also not very easy to do. The trick is that we put a inverse everything out, then the numerator becomes nicer, in the sense that this integration parameter is only identity here. So by fixing this as it's a non-normal matrix, not very nice, but identity is also commute with this non-normal matrix. So in there we can get some log comes out by integrate this resolvent. So I want to show you why logs comes out. And the integration of log, then we can somehow do the integration by part to be like put this log to the derivative part. So that's why in the end we can get d log. And this is for positive part. And by combine in the negative part, we can in the end we can show the proof. The second proof idea is the following. This integration looks similar to classical sine function, positive part, negative part, and for principal log, I want to mention that previous log are all principal log because they are complex numbers. This sine function is actually this log difference if you use the definition of a principal log. Then we do integrate on this sine function. We integrate by the log function. So again, we do some integration by part. We can get derivative of log. But we can do that exactly because this log is very fragile at the original point. So our method is to put this epsilon away, so that it's nicer a bit. Okay, but then this is not sine function. It's something like a tangent function in terms of this epsilon. Then we do this integration by part here, and then we show some uniform convergence to the sine function. That's our second proof ideas. Okay, so it's close to the time. Let me get back to our final slide. The comparison table to the all previous works. So they have different nice features for the previous work to obtain some different one-shot or bound, and there are some bounds like asymptotically tight or not. Some bound holds for uniform distribution or not. Just leave it here. And the good thing of our approach is that we accommodate all input. So that naturally extends to fully quantum ensemble. If you can prepare any quantum ensemble at your input, then you already have Beneshev Holevo's bound. And likewise, in entanglement assistant case, if you can prepare any entanglement between Alice and Bob, then use pretty good measurement, then we obtain the bound. So the proof for the fully quantum channel, an assisted quantum channel, and entanglement assisted quantum channel are almost very much similar to the CU case because we can accommodate all inputs. We can use the trick to constant composition codes that have some specific structure, type structure, and also CQSW, the classical quantum distribution Wolf coding with fixed length and variable length to obtain new operational interpretation for those quantities. So lastly, I would like to thank anonymous reviewers of Beyond ID to give us very detailed and helpful comments and suggestions to our initial draft. So with that, I thank you for your attention.
Thanks a lot for a very nice talk. Felix, maybe?
Yes.
Can you go back to the fully quantum result that you had?
Yes. Yes, this one?
Yeah, so this is the, no, like there was one where you're sharing, where it's like a fully quantum.
Fully quantum. So
This is classical
from A to B, from quantum A, system A to quantum B, and we are sending classical information only.
Oh, okay.
So it's a Holevo quantity, alpha version of the Holevo quantity.
And the error here is again defined in terms.
Yeah, it's error probability because we are sending classical information.
Oh, okay. Thanks.
So this is really like Holevo quantity.
We also have this entanglement assisted slide, no? Where it's even more fully quantum.
Yes, yeah, it's also.
Yeah, thanks, Mario. That's the one I was. Yeah, okay. So this is still entanglement assisted classical communication.
Exactly, over fully quantum channel.
Okay.
Okay, whoever was first. Huh? The other person disappeared, so it's you. Okay, can I have this? Okay, so if I understand correctly, you get this by analyzing this fuzzy Holevo-Hellstrom measurement. So you go away from pretty good measurement.
Yeah. Yes.
Does that do anything good for multi-user?
That's we don't know yet. So we have this extreme mode decomposition for 2-outcome pretty good measurement, and I'm wondering if there's something for multiple operators, the pretty good measurement for multiple operators of maybe pairs.
Like multi-axis channel.
Oh, I haven't thought about that.
Simultaneous decoding of the messages. The pretty good measurement is always a bit bottleneck.
I see. I don't have an answer. I have no time to think about this problem, but I would expect we need some new techniques because this like for point-to-point, we will need other additional technique also in classical setting as well for Mac. Yes, but we haven't tried anything yet.
There was somebody before who wanted to ask a question. No. Oh, could we go?
So you write this. Okay, thanks for that very nice talk indeed. So you write this Beigi Tomamijo
Yes.
Pretty good measurement in terms of this. I mean, you have this operational interpretation in terms of a randomized
Holevo Hellstrom, yes.
Holevo Hellstrom. Is there something similar for the standard pretty good measurement? This I didn't quite understand.
I don't think so. It's because this log derivative has this very unique.
Do you think if you modified, for example, the prior for the Holevo Hellstrom, you won't get that?
I don't know. But from a proof, this log is very special.
Yeah.
Has some nice mathematical structure. Yeah. But again, as I mentioned before, in practice, we just apply the standard one. But this is useful for analysis, for technical derivation for bounds. Mario?
Yeah, Mario.
Well, I guess we also chatted last week, but nevertheless, I'm going to ask it this anyway. So this I alpha here, right?
Yes.
So we know it's additive at alpha 1, and we know if you do a sandwiched version, it's additive alpha larger than 1.
Exactly.
But here for these paths between 1/2 and 1,
yes,
it seems not to be, or like, can you comment on that in any way?
I don't have any clue if this is additive. I guess that's the next question for us to explore, because previously we are studying a non-additivity problem for Holevo quantity, for coherent information for alpha like 1, but now I think we are ready to explore more for other alpha values. That's more problems to do.
Thank you.
I don't have a clue.
Yeah. Thanks a lot. Any last questions before the lunch? No, not lunch. Not by the way, do we have an open problem session this time? To ask questions like this? We haven't planned it, and I don't know if we have space in the schedule. At the social dinner, maybe. We can look at it. Okay, thanks again. Thanks a lot.
Thank you.